Let's talk about directional derivatives. One of the things that's so different in multivariable calculus compared to single variable is in single variable calculus, if we had a curve and we said we want to find the slope at a point, it was very easy to say what the slope meant. A slope means for every 1 unit you go in x, if you go 1 unit, what is the change in y? Well, now, when we have a three-dimensional curve, there are an infinite number of directions to be talking about. And when we find our partial derivatives, our partial with respect to x, we're saying how is this changing, but only in relation to the x-axis. When we find our partial with respect to y, we're saying how is it changing, but only in relation to the y-axis. So this idea of in single variable where we say, well, when I say slope, I mean go over 1 and up or down. The slope tells me for every 1 unit over what happens. Well, now we have an infinite number of directions we can choose from. So when we're doing directional derivatives, we have to be given almost more information than we were given before. First off, we have to have a function. And you can see right here, I've just graphed a function or an equation like this. That's no different. We were always given a function. Then I have to be given a point, right? That's no different. You always had to have a point, but we also need to be given some direction. Like, what is the slope in this particular direction or this particular direction or this? And we do that in the form of a vector. So we now are not only given the equation and the point, but also a direction, and therefore the term directional derivative. Now, the way that I would think about this is, first off, I still need to figure out the derivatives. So we have a function, it's got x's, y's, and z's. So I'm going to find 3 partial derivatives. The derivative with respect to x, and I'm just going to use kind of shorthand notation here, 2xz plus, or rather minus yz. The partial with respect to y would be 3y squared z squared minus xz. And the partial with respect to z would be x squared plus 2y cubed z minus xy. So we still need our derivatives. We are going to evaluate those derivatives at the point I was given. So we're going to plug in that point. So 2 times 1 times 2 is 4, minus negative 1 times 2 is negative 2. 4 minus negative 2 is 6. 3 times negative 1 squared times 2 squared would be 12, minus 1 times 2, so 2, 12 minus 2 is 10. 1 squared plus 2 times negative 1 cubed times 2. So we have 1 plus negative 4, which is negative 3, minus 1 times negative 1, which is negative 1. Negative 3 minus negative 1 is negative 2. So we have this kind of rate of change, 6 in the x direction, 10 in the y direction, and negative 2 with respect to z. We call this a gradient vector, at least at this point, sometimes denoted with an upside down triangle. This is the gradient of f. So we have the rates of change. That's no different than what we've always done. We've always needed to use the derivative to find the rate of change. But now this direction component adds a little step to it. And here's what I would kind of think about as you are working on these. And you have to remember the process. I mean, no different than anything we've ever done. Find the derivatives, plug in the points. But now we have to account for the fact that it's not necessarily, 1 unit in the x direction. But slope needs to have that kind of base feel of, for 1 unit, what happens? Well, this was my direction. I need a unit vector with the same direction. And again, it really comes down to the fact that slope is always for every 1 unit. What's the rate of change? Well, I need to get a 1 unit vector in that direction. So remember, to find a unit vector, we begin with the magnitude or length. So -1 squared plus 0 squared plus 3 squared. It's the square root of 10. So I can take my existing vector and we scale that by 1 over the magnitude in order to get my unit vector. So -1 over the square root of 10, 0 over the square root of 10, and 3 over the square root of 10. There's my unit vector. So I have a rate of change vector. I have the unit vector that represents the direction. And I need to put these two vectors together in a way that gives me one slope. The only operation we have to take two vectors and put them together and get one number out is to dot them. And I like to think about this as an operation because oftentimes you just need to, have a kind of a memorized process when you're on an exam or something of how to do this. And I like to think, well, I just need to come out with a number at the end, so it has to be dotting because that's the operation. But I hope it makes sense as to why this is happening. We're seeing how the x is acting in that direction, the y is acting, the z is acting, and this helps us scale the direction and kind of the weight in that direction. And that's why we're putting this together as a dot product. So if I were to do this, I would get -6 over the square root of 10 plus 0 minus 6 over the square root of 10, which gives me -12 over the square root of 10. And at the very least, this would tell you that this point in this direction, we are decreasing. And we can, of course, calculate that and figure out how much. But let me just go through this whole thing. For this curve, at this particular point, in this particular direction, this is the rate of change. And again, the process is find your derivatives and plug in the point. Just like always. We always found the derivative and plugged in our point. Take your vector that tells you in what direction, and we need that again because at any point on a 3D curve, there are an infinite number of directions you could turn. Make it a unit vector so that we can talk about slope the way we've always talked about slope. For every 1 unit, what happens? And then dot the two together. The gradient vector that represents the rate of change dotted with the unit vector that represents the direction. And this is the directional derivative. If this video helped you, please like and subscribe for more math help.